Hello and welcome to Lecture 2 of Circular Motion in Phys 1104. We spent the last video lecture looking at circular motion with constant speed. Now we're going to look at some of the modifications to those ideas that we need to be able to describe circular motion with varying speed. Let's start by talking about some conventions and a convenient choice of axes. So it's a good general principle that whenever possible, locating your axes at a point of symmetry of whatever you're trying to describe can make life easier. And so in particular, in the case of a circle, the obvious point of symmetry is the center of the circle. And so it's most often going to be useful for us to put our origin at the center of the circle. Now, having done that, the position vector at any time is pointing from the center of the circle to the object that's going around the circle. And so we have a choice of two ways to describe the location of the object. We know it's always on the circle, and so we could describe how far around the circle it has gone, a length measurement, and we usually choose to measure from the positive x-axis. So this gives us a variable that we call the arc length, which is just a distance measured along the circle from the x-axis to wherever the object is. Or we can just define the angle counterclockwise from the x-axis where the object is on the circle. Both of these are unambiguous ways of describing where the object is if you know what the circle is that it's going around on. Notice that this is actually the same as something we've already seen before. We've got a position vector, r, which is describing the location of the object relative to the origin. And like any vector, we can write it in two ways. We can write it in component form, in which case we would be giving an x and a y component of the position vector. Or we can write it in magnitude direction form, which is also sometimes called polar form. Now, throughout most of the rest of the course, component form has been more convenient. But now we're talking about an object going around a circle, so we know that the magnitude of its position vector, if we're defining the origin as the center of the circle, is always the same. It's always just the radius of the circle. And so one part of the magnitude direction form is staying the same all the time, and we only have to track the angle. And so for this reason, usually magnitude direction form is more convenient for describing circular motion because you can just focus on the angle, which is the only part of the position vector that's changing. Now, just like for other motions, we want to be able to describe the rate of change of position. And we will often want to write that as a velocity vector, just like we've always done. However, since we can always describe the object's position just using its angle from the x-axis, it would be useful to just talk about the rate of change of that angle. So the amount by which the angle changes per unit time, which would in fact be a derivative, the rate of change of theta with respect to t. Now we're going to call this angular velocity. That's not quite right. Technically, angular velocity is a vector, and this thing we're calculating is a scalar. It's in fact just one component of the actual angular velocity vector. However, for our purposes, working with motion that will always be in a plane, we don't really need to ever deal with the whole angular velocity vector. And so let's just call this thing, the theta component of the angular velocity, our angular velocity. So this angular velocity, technically the theta component of angular velocity, is a scalar. It's a component of a vector. And like any component, it can be negative. Think of what that means. If the object is moving counterclockwise, since we've defined our angles as angles counterclockwise from x, then theta is increasing, which means its rate of change is positive for an object going counterclockwise. Well, that means for any object going clockwise, so that its angle is decreasing, it must have a negative theta component of angular velocity. Further, we'll often just want the magnitude of this angular velocity, and that's what we'll call the angular speed. Angular variables are very convenient, but we often need to know the distance-related variables instead of the angular variables, and so we need to have ways of going back and forth. We'll see that in the next lecture, but let's get a start on it. Let's just think about two objects, 1 and 2. They're moving on different circles. 1 is moving on a larger circle than 2 is. And let's say they're moving at constant angular velocity. So in other words, the angle from the x-axis of each is changing by the same amount every unit time. And let's further say that their angular velocities are not only constant, but that they're the same. In other words, in a given time, if they both start on the x-axis, a short time later they've both rotated through the same angle, delta theta. Well, notice object 1 has farther to go. The arc length it has gone through is longer. In other words, if you lay a measuring tape along this curve, you're going to find that it's longer than this curve to go the same angle in the same time. And so that tells us that object 1 is going faster. Its speed is greater because it covered a larger distance in the same time. And so we see two objects with the same angular velocity will have different speeds, and that speed increases with radius. Notice the similarity to linear kinematics. In the kinematics we learned at the very beginning of the course, we would have an x component of position, x, and we would describe its rate of change as the x component of velocity. Now we have an angle, theta, and we're describing its rate of change as the angular velocity. Well, we can continue that similarity, because in linear kinematics we were constantly interested in the acceleration, so the x component of the acceleration is the rate of change of the x component of velocity. And so similarly, we're frequently going to be interested in the angular acceleration, the rate of change of the angular velocity. And you can think of them as related, the angular velocity and the angular acceleration, as related to the angle in exactly the same way that velocity and acceleration are related to position. Now, about this point, a lot of students start freaking out about all the new symbols, because these are some unfamiliar symbols. So let me just introduce them to you briefly. There's nothing to freak out about. You probably know theta, or theta, that we're using for the angle. You may not have met this symbol before. It looks like a W, but it isn't a W. It's the Greek letter omega, or omega. And that's the Greek letter that says aw. And this one here that looks kind of like an A is the Greek letter alpha. That's the Greek letter that says ah. As before, when we did this with linear kinematics, it's useful to develop an intuition for how the graphs of angle, angular velocity, and angular acceleration relate to each other, and how those relate to motion diagrams for objects moving. So let's think about this very simple angle versus time graph. Well, we know that we can draw an angular velocity graph from it because the angular velocity is just the slope of the angle versus time graph. That's what this equation is saying. And so we can look at this and see that it has a constant negative slope. And so the angular velocity versus time graph must look something like this. And then similarly, the angular acceleration must be the slope of the angular velocity versus time graph. We can see that that slope is 0. And so here's our angular acceleration versus time graph. Are you getting a sense of déjà vu? You really should. We're right back to Unit 3 of the course. Let's draw a motion diagram. This is an object that's starting at a positive angle, so at some counterclockwise angle from the x-axis, and it's moving at a constant rate. Theta is changing at a constant rate until it gets to some negative value of theta. And so the motion diagram must look something like this. note that the one difference really between this and the linear kinematics that we studied much earlier is that in the linear kinematics I stressed that we can always put our x-axis pointing any way we want. Here we're always going to work with the convention that positive angles are counterclockwise. Really, it's that there's no reason ever to work with a different convention, and there are some somewhat technical mathematical reasons to always stick with the same convention. Let's try another. Here's a pretty simple angular velocity versus time graph, and let's do exactly what we did before. So one thing is that you can see that the behavior changes at this time here. So let's drop a vertical line through. And the easier thing to do is go to the angular acceleration first. We can see that the slope here is positive and constant, and then we have a zero slope. And so the angular acceleration versus time graph must look like this. Going the other way is a little harder, but I hope you're practiced at this. We're starting with a negative angular velocity, and so the slope of theta versus t must start out negative. It goes through 0 here, and we might as well drop a vertical line there, and it becomes positive. And it's changing all through here, going from a large negative slope to a 0 slope to a large positive slope. And then it's continuing at a constant positive slope. And so the graph must look something like this. I'll leave it to you to draw a motion diagram of this. Let's check your understanding. So here we have a piece of gum stuck to a disc, and the disc is rotating, as shown, clockwise. And at this moment, the disk is slowing down. So all I want you to do is figure out the signs, positive or negative, the signs of the angular velocity and the angular acceleration of the gum. So if you're in the course, Moodle will ask you this question before allowing you to go to the next video lecture. If you're not in the course, I still encourage you to decide on what the answer is before you proceed to the next part of this video lecture.